don't want to be on video, then please turn your video off. For the hands-on part, we won't be recording, and we'll tell you when we're turning off the recording. I'm just going to give people about a minute to join from the waiting room, and then we'll make a start. We'll give people a couple more seconds to join. You can still see a few in the waiting room. And just a reminder, we are recording the session. Okay, so we're going to make a start today. So thank you for joining us. Great to see so many people online virtually. Today we're going to be looking at the Aromatics Analyser in CSD materials. So in this session, we're going to cover a short introduction, and then Joanna is going to be giving us an overview to Aromatics Analyser before leading on to a video and a demo. It will then be your opportunity to try out the tool in our Try One section of the session, and then we'll be exploring more by a quiz and a challenge before we complete the session with a summary and wrap up. So things you need to know for today, just a reminder, we're going to be recording the first part of today's session. So we won't record the hands-on part, and we'll let you know when we stop recording. If you have a question, I can see some people can't hear, but others can. So I'm hoping that other people can hear. Please let us know if you can. If you have a question, please type it in the chat box, which I can see people have already found. And to get us all using the chat box today, we're going to be asking you to tell us what your first record, CD or cassette you bought or received was. So now's your opportunity to tell us what your first record, CD or cassette was, so we can all get to use the chat box. I think everyone's shy in telling me their first cassette. Queen Greatest Hits, Will Smith. I can start to see a few. Aha. So this part you'll be on mute because we're recording, but then feel free to ask us questions verbally for the hands-on part as well. For the hands-on part, you'll need CSD materials installed and a license activated, as well as the workshop handout. You should have received an email from us on the 19th of November, and it's also available on this website on their slide, which we'll also post in the chat box. So we have designed this workshop for people who have already used Mercury before, so we won't be going over the basics of Mercury, but we did do that in the last workshop, so that recording is available to you. So what do we want to learn today? So why you'd want to use the Aromatics Analyser, familiarity with the Aromatics Analyser interface, how to distinguish favourable aromatic interactions in a structure, and about different orientations of aromatic interactions in a crystal structure. And you can read more about some of these terms in the dictionary at the end of the handout. So who are your tutors who are here to help you today? So alongside myself, I've got Joanna, Andy, Eva, Ilaria, and Natalie and Jinka. So please do feel free to ask us questions as we go through today, and we'll be happy to help you. So that's a bit about us, but we want to find out a bit more about you, like we have in our other workshops. So have you ever attended a CCDC workshop before? Have you attended some of our CCDC virtual workshops? Have you visualized or explored crystal structures with Mercury? Have you collected or refined your own crystal structure? And have you deposited the structure with CCDC? So hopefully you'll see a poll pop up now, and please select all that are true while I look to see what other CDs and cassettes people got. I can see you starting to add in details to the poll. And it's great to see that most of you have explored and used Mercury before. Okay, we'll give it a few more seconds for the last people to add their information. Okay, so it looks like the winner is using Mercury before, which is great. Some of you have already used CSD materials, and a lot of you have collected and refined your own crystal structures before. So back on the slides. So just a reminder, at the CCDC, one of our primary aims is to curate the Cambridge Structural Database, a database of over 1 million structures. And today we're highlighting this golden ring structure that was published in 2019 because it's very pretty and it's got some aromatic rings in, so perfect for today's session. So the CSD includes structures from published articles, patents, university repositories, and thesis data, as well as data published directly through the CSD as CSD communications. We've seen this before in our workshops, so it's a database of organic and metal organic crystal structures. It's got a range of different information and different types of structures. It's also got some wonderful aromatic structures. So here are two of the most aromatic structures in the CSD. And here are some of my personal favorite aromatic structures in the CSD. So we've got some interconnected aromatic structures or aromatic molecules as well. So let's explore some of the chemistry behind what's in the CSD a bit more. And today, in line with the theme, we're looking at the most common elements bonded to aromatic rings. So unsurprisingly, you can see that hydrogen is one of the most common elements bonded to aromatic rings, closely followed by carbon. So a very brief background to the CSD. What we'd want to do now is our second poll of the session, asking you what kind of structures you're interested in applying the Aromatics Analyser tool on. So is that organics, metal organics, proteins, or other? And you should start to see the poll now. And the second question is, what fields would you like to apply the Aromatic Analyser tool on? So pharmaceuticals, semiconductors, agrochemicals, or other? So we're starting to see quite a few votes now. It looks like organics and metal organics are vying for the lead, and pharmaceuticals and other in the fields that you would apply. So we'll just give it a few more seconds. Okay. And we'd be interested to hear what other fields you will be applying Aromatics Analyser to, so do feel free to pop us a note in the chat channel as well. So at the CCDC, alongside the CSD, we produce a number of different software suites to allow you to gain the most from the data that we hold. So allowing you to visualize, analyze, and gain new insights for the data. And today we'll be looking at the CSD materials version of Mercury, which is in our CSD materials portfolio. And I am now going to be passing you on to Joanna, who's going to tell us more about the Aromatics Analyser tool that's available through Mercury.
Hello everyone, thank you Suzanne, and I'm sharing the screen with you now. Let me know if it's going full screen. Can you see my screen now? Yes.
Yes.
Welcome everyone to our Aromatics Analyzer workshop. You can access the Aromatics Analyzer in Mercury. Just select the top level menu, which is the CSD materials, and then simply click on the Aromatics Analyzer. This will allow you to assess the strengths of aromatic interactions in a crystal structure. If you are an academic, you should have access to a CSD enterprise license level and be able to access the tool. If you work in industry, you should have a CSD material license level to be able to use the tool. A brief overview of what I'm going to tell you today is how and why we build this tool, how we build it, and then as Suz mentioned, you will see some how-to video and some of our workshops later. As you are quite familiar with our tools, but as Suz mentioned, we provide you with a bunch of solutions that allows you to analyze and visualize new materials that you generate. And this was all possible because we lie on top of very large and highly accurate database. So we can then use all this knowledge-based software to analyze your structure. And for example, if you look in this under the CSD materials, you could use full interaction map to assess whether your hydrogen bonds interactions are satisfied or not. Or another example is Mogul, where you could look at the bond distance and angles to assess whether what you find experimentally is in accord with what's on CSD or if something is flagged up. And some of you probably are familiar with hydrogen bond propensity, which allows you to assess the likelihood of hydrogen bond interaction in a crystal structure. And if you want to get a bit more familiar with this tool, we have a dictionary at the end of the handout, which you can check. And we will also mention this tool a bit in the workshop today. But the example I want to show you here is it's ibuprofen. This material has two polymers, and both of them have the same hydrogen bond network. They form a carboxylic acid dimer, as illustrated in this picture. Now, the hydrogen bond propensity will plot both of these polymers from the lower point on the chart in here. So this is the limitation of the tool. If you have the same interactions, you cannot really distinguish between them. What you can use this tool for is to look for resistance for OH, O interaction or OHN. But how can we analyze those type of structures and polymorphs further? Well, we could look at other type of interaction. For instance, you could look at weak van der Waals interactions, such as CH3 or halogen bond interactions. But how about we look at the aromatic interactions? Now, the aromatic interactions compared with hydrogen bond interactions are non-linear dependent. So in hydrogen bond interactions, if you move farther apart, the interaction become weaker. That's not the case for aromatic interactions because distance doesn't really matter sometimes. Due to the fact that you can have T-shapes orientation of these interactions, or they can be parallel displaced. And for that reason, we couldn't really use previous information from CSD to build the tool. What we had to do is to generate benzene dimers and orientate them in different positions and different distances and try to cover as many space as possible that will replicate what you will have in a crystal structures. So when you come with the new structures, we'll cover all those positions. Next slide. And for all these dimers that we generate, which was a large number, about 25K, we calculate the energy. Then we calculate the molecular descriptors such as centroid distance, as well as atom distance. And then we use a machine learning technique such as deep neural network to learn from all these informations here and predict those aromatics interactions. Now, because we're predicting this energy, we didn't want to put them in as to claim that we are calculating some DFT energy. And for that reason, you will see in the tool, we introduce a score. And this score is based on a linear score when you plot this score here from 0 to 10 versus minus 16 to 0. So our lowest energy for our dimers we found was minus 16 kilojoules per mole, which stands in the tool for 10 as a score, and 0 kilojoules per mole in the tool will be standing for 0. This is how the tool looks in practice. You can just simply select your molecule in Mercury, then this button here will be enable, and then you simply can click calculate. And the tool will give you information about all the centroids. They will all be labeled and populated in these two first column here. You will also have information about the centroid distance in here, as well as relative orientation, which will give you information about whether you have a T-shape or parallel displaced structures. And this is based on normal to the ring angle. You also will have information whether your interactions is inter or intra. Sometimes you have more than one aromatic ring in your structure. You also will be provided with a score, as I mentioned. In this case, 8.1 is the highest, but you could have anything between 0 and 10. You'll also have an assessment whether your interaction is strong, moderate, or weak. And you have all this information in Mercury. When you open the menu, if you will hover over the table headers, all this information here will be displayed. What is in terms of energy, or if we talk about strong interactions, it's everything above minus 11.2 kilojoules per mole. Everything between 11 and 4.8 will be a moderate interaction, and anything below minus 4.8 kilojoules per mole will be a weak interaction. In your hands-out workshop and in our how-to video, you'll hear more about what this lower menu here is doing and how can you use it. Today in your workshop, you will work with 3 systems, such as bicalutamide, which has 2 polymers and they have different hydrogen bonding. Paracetamol, we select 2 of its polymers and they have the same hydrogen bondings. And tesaglitar, which has been developed from a less favorable hydrogen bonding network. Now my colleague Ilaria is gonna show us the how-to video, which you can also find it on our YouTube channel. And she will play this for us, and then we will have a live demo in Mercury how to use the tool. Now Ilaria is trying to share the screen.
To begin, simply launch the program by clicking on the icon. When the Mercury program loads, you will notice a list of ref code in the right-hand side of the structure navigator. This represents all the structures in CSD. The molecule that we will be investigating is paracetamol. To browse the structure, simply type its ref code in the search box. The ref code we will be using is HXACAN01. You will see that the molecules appear in the Mercury display windows. To calculate and visualize the aromatic interaction, simply choose CSD materials from the top level menu and then select Aromatics Analyser. A dialog box appears, which is guiding you to the required steps. First step is to select all the atoms in just one molecule. To do that, simply hold Shift and right-click on the molecule in the display window. Now you are ready and you can start to calculate the strength of aromatic interactions between these molecules and the molecules that will be generating around it. To do that, simply hit Calculate. This generates a packing shell using a distance of radius of the sum of the van der Waals radii plus 5 angstroms. As you can see, the table in the display box is now populated. To find out more about what each columns represent, hover over the table header and an information text will be displayed. A centroid for each aromatic ring in the packing shell is displayed and labeled. Hence, you can identify each final dimer's interactions in the generated packing shell. For each aromatic interaction, a set of parameters are calculated, such as centroid distance, the angle between the ring normal, whether the interaction is inter or intra, and most importantly, as you can see, a score and an assessment of the interaction strength. The score is displayed from 0 to 10, indicating whether the aromatic interactions are strong. That will be between 7 and 10. Moderate between 3 and 7, and weak between 0 and 3. The table is interactive, and you can identify in the display window each particular interaction. To do that, simply click on the row of interest. The dimer will be highlighted, and you can notice that the centroids are now displayed in turquoise. The tools allow you to exclude symmetry equivalent interactions or to include intramolecular interactions when applicable. To do that, simply toggle on the display box. You can export the outcome in a CSV format, or you can find more about each atom in a particular interaction. To begin,
Right, so now we will have some hands-on demo in Mercury. You can follow with me along if you wish. I'll probably go quite quick, but it's just if you want to follow us. Also, you'll have the opportunity later to play in Mercury during our workshops. So we'll be looking to demo two systems, phenatoin and estron. And I'm gonna share my screen now, which is Mercury. Share screen. I guess you can see my screen now. All you have to do is to open your Mercury from your desktop windows. I already have this open. And you have here on the right hand side the structure navigator with all the ref codes. So if you look at the first system, which is PHYDAN01, you can notice that we have two aromatics ring here. What the tool will do will generate a packing shell around, and you will have all the interactions between these aromatic rings and everything in the packing shell. So if you go to the CSD materials and select the Aromatics Analyser here, now what you have to do is to select the whole molecule. You can also select just a bunch of atoms, but then that will affect the packing shell that's built around. To select the molecule, if you hold Shift and left click on the molecule, now you have this selected. You can notice the Calculate button became enabled, and you could just click on Calculate. And this will generate a packing shell of van der Waals radio plus 5 angstroms around this molecule. And you will see how this table here is going to get populated with all the calculations and values. Now you can see we start from this molecule here. You see the ring is labeled 2 and 1. So this was our molecule that we start from. And you will see all the centroids labeled in the first column here. And then in the second will be all the aromatic rings they interact with. This tool is quite powerful because you can immediately see clarity out of complexity. So if I, for instance, change everything to wireframe, this table is interactive. So I can, for instance, just click on the first row. This will highlight all the rings in yellow, as you can see. And then you can change them back to caps lock. And you can see quickly what this first interaction in the row is, what shape it has. You can see it's a bit of T shape, and you could see that reflected in the relative orientation. Now this system has about 48 aromatic interactions, as you can see, and you have 4 of them labeled as strong. And this will kind of inform you that probably the top 4 of them will have a substantial contribution to the overall stability of your crystal structure. You can see the relative orientation also for those strong interactions. Most of them are kind of tilted and T-shaped, and when you have moderate, in this case, you will have more parallel displace orientation of your aromatic rings. As you've seen in the video, if you hover over all these tables here, you will see a score, an assessment, what this assessment means, everything. And when you have more than two aromatic interaction in your crystal structure, as I said, sometimes you will have intermolecular pairs that you want to look at their strength. And if they will be intramolecular interaction, they will be labeled here as no. As default, they are not included. So if you want to include them, all you have to do is to toggle on this box here. Also, if you look at this third and fourth row, you can see all these values as identical. What this means is that these interactions are actually built based on they are symmetry equivalent. So if you want to exclude them, you will have to toggle on this box here. I think the how-to video was a bit quick, and you can see how you can export all this information in the table as a CSV file here. As well, if you select one of the row that you are interested to find out more with about the information of the atoms in these rings, you can see all the distance between those rings and the adjusted van der Waals distance in here. Now, if we look to another system, you don't need to close the display windows, you can leave it open. I will type the next system, which is ESTRON11. Now this system here has only one aromatic ring in here to which we will be looking how it interacts with other rings in the packing shell. Everything is still available from the previous calculation, so you should bear in mind to always look what ref code is displayed in the header here, and that's what the results are for. So you should bear that in mind. So if I select this molecule now and then hit calculate, you will see the ref code will change as well as the table once the calculation is finished. And this is in general quite quick in Mercury. Sometimes if you share the screen, it's a bit slower, but here you go. We have now the table. So you can see for this system, we have 12 interactions. And what is quite unique about this system that all of them are weak. So what you will conclude in cases like this is that you don't have major contribution of these rings to the overall stability. So because they're all weak, so will not have a major impact on the overall crystal structure stability. Now it will be your turn. My colleague Ilaria is going to start sharing the screen and give you more information about the workshops and what you are going to do next. Back to Ilaria now. Thank you.
Great, thank you, Joanna, and I'm afraid it's me again. So we're now going to give you about 40